Okay, so today we're going to talk about, like I mentioned, how entropy affects colligative properties. So for the first thing I want us to think about is the nature of solutions, okay? So if we have a solution, and we can think about an aqueous solution, okay, as compared to pure water. So if we have pure water, right? Pure water is in the example over here at the left. And both of the images on the left are examples of pure water. The one up top illustrates the equilibrium between the vapor and liquid phase. So we have a vapor up here and a liquid down there. And the one on the bottom illustrates the equilibrium between the liquid and the solid phase. Okay, so in the first one, if you think about the vapor pressure of a solution, right? There's this equilibrium that occurs where the liquid particles have enough kinetic energy to break through those intermolecular forces at that surface of the liquid and go into the vapor phase. But those vapor particles are moving around and will occasionally collide with the liquid. And when they collide with the liquid and stick, then that means that they're going to the liquid phase. So there's this equilibrium between the two phases. And this is something that can be affected by having solute particles in the solution. Right? So when you have solute particles in the solution, something happens that throws that equilibrium off such that more vapor particles are going to stick to the solution, right? So you're going to lower the vapor pressure, right? So that was one of the things that we looked at, right? Vapor pressure lowering. And remember vapor pressure lowering, because if you lower the vapor pressure, you have to raise the temperature at which that substance is that substance boils at, because the definition of boiling, remember, is the temperature at which the vapor pressure equals the atmospheric pressure, the pressure above that liquid. And so vapor pressure lowering and boiling point elevation go hand in hand. Okay. So that's one of the phase changes we're going to look at, and how a pure solvent like water differs from a solution like, say, a sodium chloride solution. The other one that we're going to look at is the phase change between solid water, right, where you have, say, solid ice, and liquid water. Okay. Now, in the pure solvent, right, pure water diagram here, there are no solute particles, and so you have this equilibrium where those the particles are coming from the solid state and going into the liquid state, and then some are going from the liquid state and going back into the solid state, and if they hit, they become part of that ice crystal. It's crystalline solid. But something that we know is that when you add a solute, the addition of the solute causes the freezing point to get lower. So that was our other colligative property that we're going to talk about. Okay, so it's freezing point depression. And so freezing point depression comes about. Essentially, you have to lower the freezing point in order to get that substance to crystallize. So you have to take away more energy from it. Now, as we set this up, there are a couple of key things to think about with pure water as compared to an aqueous solution. Okay, when you have pure water, the liquid phase is all water, right? Also, in the vapor phase, that's also all water. In the solid phase, although those particles are packed really closely together, it's still all water. Okay? But if you have a solution, okay, now what we can think about is how does the solution differ here, right? In the liquid phase, you have an aqueous solution, right? And so that's, remember, a homogeneous mixture. But if you think about an aqueous solution that is in equilibrium with the vapor, so you have liquid and, excuse me, you have the aqueous solution and the vapor of that water. So we can think about the vapor phase. Well, here we're talking about non-volatile solutes. And so in the vapor phase, it's all water still. Okay? And if we look at our equilibrium between the solid and the liquid, or the solid and the aqueous solution, so in the solid phase, it's again all water because the solute particles don't crystallize with the water molecules to make that ice. And so the biggest change here, right, is this liquid phase, right? Whether it's the aqueous solution or the pure liquid water. Okay, and that's how I want us to start to think about the colligative properties and how the colligative properties have a difference here compared to the colligative properties of a solution have a difference from the pure solvent. And so that's our initial frame. Right? It has to do with how the liquid water differs from the aqueous solution. Okay? Now let's start thinking about this from the standpoint of thermodynamics. In particular, delta G, right? Remember, delta G is equal to delta H minus T delta S. Okay? And so what we're going to look at here is how do we know that we would have boiling point elevation or freezing point depression? And so something to think about is the sign of the delta H, right, and the sign of delta S. So if we think about something like the boiling point elevation, we're going to start by thinking about boiling point elevation to frame this. So what we're talking about with boiling point elevation is we're talking about a delta H of vaporization, okay? And if we're vaporizing something, remember vaporization is an endothermic process. We have to put in energy in order to get something to vaporize. So that delta H of vaporization is going to be greater than 0, right? This is endothermic. Okay? Now, when we think about the delta S for this process, so delta S of vaporization is also going to be greater than 0 because we're turning a liquid into its vapor, right? And so that is going to lead to an increase, right, in the entropy of the substance that we're looking at. Now, based on what we talked about before, if we have a positive value for delta H and a positive value for delta S, then we're going to find that this particular process will be spontaneous at temperatures that are high, or at temperatures above some temperature T. Now, we're not going to get into this quantitatively right now. I want us to think about it more qualitatively. So what we do know is the temperature above which this is going to be spontaneous is easy to calculate, right? That temperature is calculated when delta G is equal to 0, right? And so you can say, okay, so that would be when 0 is equal to delta H minus T delta S. And the things that we're going to look at in here are the delta S and delta H in order to figure out why would this process find or leave us with a T, right, that is higher, right, for a solution than for the pure solvent. Right, that's the idea of boiling point elevation. Okay, so that's sort of what we're talking about here. And so for this, if you rearrange this equation, you'll find that you get the temperature is going to equal the enthalpy change for this process, so delta H of vaporization, over the delta S of vaporization, the entropy change. Okay, and so something about the change in enthalpy and the change in entropy will lead to there being a higher temperature for the solution as compared to the pure solvent. Okay, and that's sort of the next thing we're going to diagram out. If we think about it, so what we're going to do here is we're going to set this up such that we have on the left-hand side, we're going to talk about the solvent. Okay, and on the right-hand side, we're going to talk about the solution. Okay, now a key to this is I want to talk about two things. I want to talk about the delta H, right, or the change in enthalpy for this, okay? And we're going to talk about the entropy, okay? And we'll do that for both of them. And we'll kind of take them one at a time. And so what I want us to think about is sort of on the scales here, okay? So here's our enthalpy scale for the solvent. We'll just start with that, with the solvent and solution and their enthalpies. So one of the keys here is we're actually going to talk about both the different sort of phases, and we'll look at all three phases here. Okay. The thing that I want to start with is if we go, remember, we go back up here and we say, okay, little keys that we can do for both of these are that in the vapor phase, it's all water, and the solid phase, it's all water for both an aqueous solution and for pure water. And we're going to start by putting both of those things sort of at the upper and lower bounds of our two graphs. So we can come up here to, let's say the top here is my water vapor. And way down here at the bottom, we'll call that our solid. And that's going to be, I'm going to try to draw this as easily as I can here, right? So we'll have solid and vapor. Okay. So when we think about the enthalpy or the enthalpy change going from, say, a solid to a vapor, that enthalpy change are the same for the solvent as it is for the solution, because we're talking about the two different phases that aren't different from each other. The big difference here, and we'll put this sort of in the middle for the pure solvent, that's going to be our liquid. Okay. And so if I go from the, and this is, again, our solvent is just water that we're talking about, okay? Now, if I think about the change in the enthalpy from the liquid to the solid, that's the delta H of vaporization for water, okay? Now, that delta H of vaporization depends upon sort of where does that liquid enthalpy fall? Well, that's just the enthalpy of, you can look at that as the enthalpy of formation of water compared to the enthalpy of vaporization, or excuse me, the enthalpy of formation of liquid water versus the enthalpy of formation of water vapor. Basically, you're talking about going from liquid water to water vapor, okay? Now, when it comes to freezing, right? In freezing, we're looking at a process that's the other direction, but it's going from the liquid to the solid state, okay? And so that right there, right, is the delta H, okay, of fusion, right? Only it's the negative of the delta H of fusion, because the value for delta H of fusion, remember, fusion is melting. So we can think about that as delta H is of vaporization versus delta H is of fusion. So on the solution side of this for the enthalpy, the question is, where does the enthalpy of a solution of, say, sodium chloride that's aqueous lie compared to the enthalpy change, or the delta H, or the enthalpy of that liquid, okay? So if you think about it based on just the solubility of sodium chloride, there's actually a very, very small difference in the enthalpy of a solution as compared to the enthalpy of the liquid for sodium chloride dissolved in water. It's a little bit higher, right? It's just a tiny fraction higher, but they're very similar, right? Right, so you can say a similar enthalpy of, similar enthalpy for the aqueous solution. I'm going to call this the aqueous phase. And we're going to call it aqueous sodium chloride. So you're going to have the similar enthalpy for the liquid water as you have for sodium chloride. And so basically, if you look at the delta H of formation or really the enthalpy of the change, the enthalpy of solution, right? So when you dissolve sodium chloride, how much energy is there? There's really only like a 4 kilojoule per mole change to the enthalpy of the sodium chloride dissolved as compared to the sodium chloride solid compared to the it not being dissolved, basically. And so essentially you have, if you look at the enthalpy change from the aqueous sodium chloride, right? So we can call that delta H of vaporization for NaCl, okay? That's gonna be similar to, okay, it's very close to, right? The enthalpy of vaporization for the pure solvent. So you can say delta H of vaporization for water it's pretty close. It's not exact, it's about 4 kilojoules per mole, but in the grand scheme of the enthalpies of those solutions, it's pretty small. Okay, so that doesn't change much. It's about 4 kilojoules per mole, and it's an endothermic change. The actual, if you actually look at the numbers of it, the delta H for the solubility of sodium chloride is actually a positive value by a small amount. Okay, so they're similar. What you then find is if you look at the entropy change for these two things. Okay, so again, we're gonna start with our vapor because that's what we have in the vapor phase is water vapor. And in the solid phase, we have water as a solid, ice. And since that's just pure water, in whether we have a solution or whether we have a just pure solvent, we can put those points at the same point. Oop, that's not what I'm doing. Try this again. Okay, so we have these sort of at the same places because they're pure solvent, whether they're solid or vapor. Okay, and so we'll start again with, and mind you, remember these are just qualitative, they're not to scale or anything like that. We're just kind of thinking about why does this work the way it does. So here we have, again, the pure liquid. Okay, and so if we look at that entropy change for the liquid to the vapor, that's going to be a positive entropy change, right? So that's going to be a delta S of vaporization for the water. Okay, and if we were looking at the freezing of water, you'll have delta H, or excuse me, delta S, back to that, delta S of freezing of water. Okay. And so the big change, the big difference here is, well, what happens to the entropy of the system when we add that solute to it? And if you add a solute to the water, you would imagine, well, now you have solute particles that are dissociated. And you can think about it this way too. I want to make sure I'm phrasing this in the right way. If we look at this as being the difference between just pure water and the sodium chloride, you can kind of think about the pure water as being pure water in and of itself, and then sodium chloride crystals by themselves. Now, when you put the sodium chloride crystals into the water, you've changed the entropy of that solution, because those sodium chloride crystals are now dissociated, but not just dissociated, they're interacting with the water molecules together because of the solubility and how the substance dissolves, okay? And so what you can think about here is the entropy of the solution is going to be significantly higher than the entropy of the pure solvent. And so over on our solution side of things, we can go over here and put a line at a higher location for the aqueous NaCl. Okay, which means if we think about the change going from an aqueous solution to vapor, right, that's going to be our delta S of vaporization of this sodium chloride solution. Okay, now before we go and start to put these together, and we'll start to put some of these together on the next page. If we look at the enthalpy of fusion, well, the negative of the enthalpy of fusion, right, for water compared to the solution. Again, that's going to be a similar change to the enthalpy of fusion for the pure water solution. But if you look at the entropy change, right, for a substance freezing, that delta S of freezing, right, for the sodium chloride solution, that's going to be a much bigger entropy change for that sodium chloride. So on our next slide, we're going to kind of put these together a little bit. Okay, so if we think about the delta H of vaporization for water, pure water, that's going to be similar to the delta H of vaporization of sodium chloride. And the change in entropy for vaporization of water will be greater than the entropy of vaporization of sodium chloride solution. Okay, that's our first step. And if we do the same thing for freezing, delta H of so negative delta H of fusion, so we'll call that here delta H of freezing, is going to be approximately equal to the delta H of freezing, and this should be for water, so then is going to approximately equal the delta H of freezing of the sodium chloride solution. Okay, those are going to be very similar to each other, and something about these, right, these are both going to be with freezing as a process, right, exothermic, right? Right, so those delta H will be less than 0 or negative. And then we have our delta S of freezing of water. Here, right? This is going to be such that the entropy change in freezing water is going to be larger for the solution than it is for the pure solvent. And just as a reminder, right, we're talking about going from the liquid phase to the solid phase, so the delta S of freezing is also going to be less than 0. So in both of these cases, we're looking at what happens either above or below a certain temperature, and we're looking at that temperature cutoff in particular. So if we think about the for freezing and vaporization, remember T. Okay, so T is equal to delta H, right, so vaporization, over delta S of vaporization, right? And then the T for the freezing is going to equal the delta H of freezing divided by delta S for freezing. Okay, now if we look at these, the important part here, because remember, that's going to stay very similar value. The important part, so we can say it stays nearly the same. And it does so in each case, right? So that stays nearly the same here. Okay, so the important thing in this whole piece is the magnitude of the entropy change for these phase changes. So since the delta S of vaporization for the sodium chloride solution is smaller than the delta S of vaporization for pure water, the temperature at which the solution boils will be higher than that of the pure water solvent. Right? And so you can think about this, right? As the numerator as the denominator gets smaller, right? As the denominator gets smaller, the T gets bigger, right? So if the delta S of vaporization for the solution is smaller, then that temperature at which this process happens must be higher. And sort of the opposite of that is true for freezing, right? If you go and look at the freezing entropy, okay? And you can think about this now as, so if you look at freezing, both of these are negative values for the enthalpy and entropy. And so the temperature change, like the negative values for the entropy and enthalpy cancel out. And so you're still just saying, you're just dividing out enthalpy and entropy in this case also. So you're really interested in just the magnitude of that difference here. And so since the entropy of freezing of the sodium chloride solution is larger than the entropy of freezing of just the pure water, the temperature at which the solution freezes will be lower, right? So the delta S is larger there. Therefore, the temperature will be smaller. Okay, and so that's your actual thermodynamic explanation for the colligative properties of boiling point elevation and freezing point depression. And I'm not going to get into osmosis, but those cover, it also covers sort of vapor pressure lowering as well, which is related to freezing point, which is related to boiling point elevation. Okay. And so with that, I'm just going to stop the recording. That's our special topic. I just kind of wanted you to see how this thermodynamics can be used to explain the these colligative properties. Okay, and that's